All right, hello everybody. My name is Mark Ebersol. I'm the CUDA educator here at NVIDIA. I'm going to help kick off this first office hours we have in this deep learning course before I turn it over to our deep learning experts to help answer your questions. I just want to make sure everybody understands what this office hours is about. The purpose of this is to help answer any questions you may have had that were unable to be answered in the previous week's class, as well as any questions you may have come up with over the last week while working on the associated hands-on lab. So this is the first time we've done this type of office hours, so feedback is always appreciated. You can use the DL course alias you've been getting emails from after the office hours if you have some feedback on it. We're going to do all questions as chat-based questions. We have John Barker on the line again, and he will be answering a few of these select questions verbally, as well as some questions we had from last week. We also have a number of our deep learning experts online to help answer questions over chat. So as you ask questions, they will be responding to you through the chat window. And we're going to make sure to include both the question and the answer in one chat comment so everybody can see. We got that feedback from last week. All of these chat questions will be made available in a document also after this, so you can peruse them offline in addition to the recording of this office hours if you want to hear the verbal responses as well. So please, if you do have questions, we'll do them on the chat channel here starting shortly. What we have up is the schedule of the labs of the course. So the idea of this course is every 2 weeks we're going to have a new class with new content and a new associated hands-on lab, so you can actually work through the material. And then we'll have a follow-up office hours like we're doing today, so we can help answer any questions you may have gotten on each of these contents. Right now we have 5 scheduled classes. This is the end of the first one. Given the popularity of this class, we are looking into doing more advanced content once we get past the 5th class. So please stay tuned for information on that. I'm also going to show you a useful links slide. This is just I can get it up. There we go, the useful links slide. So this is just some useful links we're going to leave up during most of this unless we have some slides to show you from last week. This first link is the important one for this class. This is where we're going to post all recordings, all links to the hands-on labs, any documents associated with the class will be posted on this site in addition to the schedule. So if you ever miss a class, you want to see the recording, or can't remember which lab is associated, you can go to this link. I also have the recorded presentations link. This is essentially every talk and presentations from all the conferences in the past that NVIDIA has been involved in that we've been able to record is put here. This is a great resource for looking up expert talks on a variety of topics having to do with GPU computing, from specific tools usage to research into various aspects. So this is a really great resource to go to if you were looking for past recorded conferences that you weren't able to make. The third one is our Parallel for All blog. This is run by our Chief GPU Computing Technologist, Mark Harris. This is a technical blog. We try to keep all the marketing stuff off this blog and just keep it very technically focused. In fact, we just ended with a great 3-part series on using Ciano for neural network translation. So you can go check that out at the Parallel for All. I encourage you to subscribe to this so you can stay up to date on the latest happenings in GPU computing. And then finally, I encourage you to become a registered developer at NVIDIA for the GPU computing program. We try to keep spam and marketing to a minimal with this. This program is essentially our way of communicating back to you for interesting things happening in the fields you are interested in. It also allows you to file bugs to the engineering team to get early access to software. And it's just a very useful program if you're going to be doing development with GPU computing. So now I am going to turn this over to John Barker. He's going to kick off by answering verbally some of the questions we had from last week, some of the more common and popular questions. And at this point, you can start asking questions through the chat, and then our experts will begin going through and answering them through the chat. And if any of them are high value or we feel everybody should know, we will transfer those over to John so he can answer them verbally as well. All right, John, go ahead.
Great, thanks, Mark. Good day to everyone again. If you didn't hear me speak last week, my name is John Barker. I'm a solutions architect with NVIDIA. As Mark said, I'm going to kick off the session today by answering a few of the commonly occurring questions which we didn't necessarily cover last week, and I'll add a few more of those in as we go through in between the questions we get in chat today. A very common question we received related to an early slide that said, are we proposing that deep learning completely skips feature engineering and there's no need for input from domain experts? Definitely the advantage of deep neural networks is that they automatically learn features relevant to the training data and to the task that you're trying to solve with the data. And in most cases where you have raw data like inputs, images, speech, natural language, this can drastically outperform hand-engineered features in terms of accuracy, predictive accuracy for tasks. That doesn't mean that deep neural networks are going to replace domain expertise. It really just moves where you apply the domain expertise and the level of effort involved in applying that. So domain expertise is still critical in making decisions such as choosing the right training objective for your deep neural network, coming up with physically plausible data augmentations which will help your network generalize and avoid overfitting. But these choices are in some sense much less manually labor intensive than handcrafting features, so it's a more scalable approach to using your domain expertise. Okay, a second question we received, which was asked a lot, was how do we choose the number of layers in a network, and is more layers always better? Choosing network architectures is today more of an art than a science. Ultimately, the way that we should be doing this is that we also optimize the network structure and learning parameters in the same way that we optimize and learn the actual network weights. In practice, the best way to do that is still a research topic, and in many cases that wouldn't be computationally feasible today. So the recommended way to choose your network structure is to look for an application that uses similar data, similar volumes of data, and has a similar objective to the task that you want to apply. Start with that network structure. And then, as Jeffrey Hinton says, if your network isn't overfitting, it's not large enough. So what we mean by that is you should make your network, keep making your network larger in terms of number of layers, number of neurons in the layers, until you're performing very, very well on your training data set. And then you can start to think about controls that you need to put in to prevent overfitting, which means that you're very good in your training set but not good on generalized test data. A kind of more general answer would be as well that by putting more neurons into a network and more layers, you can learn a more complex functions more efficiently that map raw data to your objective. So when I say if your network is not large enough, if you're not overfitting, I literally mean that you would want more neurons, more layers. And a third question, just to get us kicked off, is there a way to map back from the predictions from a neural network to identify what features in the original input is important for the task at hand? This was a commonly asked question, and the common criticism that's leveled at deep neural networks is that they're a black box technology. It's very hard to understand what is going on, what has been learned by the network. So there are methods for running the network in reverse, if you like, where you take a particular top-level neuron that corresponds to, say, a class in your object recognition data set. So let's say you take the dog neuron, and then you can map back through the layers to find the stimulus which would maximally activate top-level neuron from each of the layers. One method for doing this is called deconvolutions, if you search for that. But there are other methods too where you try and generate synthetic inputs to the network which maximally activate the neurons, or you find the examples in your training set which maximally activate the neuron corresponding to a particular class. In addition to that, digits, which we talked about, the NVIDIA graphical interface to the Caffe deep learning framework, also offers visualizations of the activations in the different layers of the neural network as you input different training samples, and this can be useful for kind of getting a qualitative feel for which features in an image are important for it being classified in a certain class. So at that point, I'm going to move on to start answering some of the questions we've had coming in from chat. So one question is, could you compare the computation complexity between training and deploying a deep neural network? We talked a little bit about deployment at the end of the last webinar. I'll just show the chart we showed there. And what I said was that the training development of a network is a task that typically requires computational resources for hours to days to even weeks, and there's very large benefits from GPU acceleration. This is not necessarily because the feed-forward complexity of putting a data sample into the network is computationally more complex than when you test a new data sample. Those are exactly the same operations. It's because the back propagation, where you update the weights, adds additional computation to that feed-forward step. Although it's a comparable amount of computation per input data example, the main difference in the amount of computation done for development and deployment is that when you're training a network, you will input the same training image typically thousands of times. We call these training iterations or training epochs. So whereas when you test a new image, you simply input it once. So that's where that difference in computational complexity comes from. There's another question here that says, does the size of the input data, the number of pixels, for example, need to be the same for all training data? If not, how does the size of the input layer correlate with the size of your training data? Typically for convolutional neural networks and artificial neural networks in general, you do ensure that each of your input data samples has the same dimensionality. The reason that you do this is not that you couldn't accommodate different dimensionalities at input that you then in real time standardize for the mapping to the for the activation to the first layer of the neural network. The reason you do it is because it's then possible to train the network in batches of images or input data simultaneously in what we call mini-batch training. The benefit of doing this is that you can vectorize the network activation operations and as such leverage parallelism from GPU acceleration, so you can train much more quickly by doing so. So this obviously presents a challenge in the case of, for example, images. If you want to download a large data set of images from the internet and use those to train a neural network, they're probably not all going to be the same size. So there's a couple of ways that people typically handle that. One is that you pre-process your data to make all of the images the same size, and there are many different operations you could choose to do, image processing operations you could choose to do that by, for example, cropping the images or stretching them, or changing the standardizing the dimensions and then padding, but keeping the aspect ratio the same and padding any then subsequently missing pixels with with noise, for example. Although often what people actually end up doing is training the network on small image patches that are randomly extracted from the actual input images. And this is actually helpful for training a network that is more sensitive to detailed local structure as well. Okay, I'm going to jump back to a couple of the questions from last week again. So one question specifically related to this course was what prerequisites are there for the remainder of this course, and what math background is useful for this course or for learning deep learning in general. So there are no prerequisites for this course. We'll be taking a very practical approach to using available deep learning software frameworks and tools. The idea is that if you take this course, we should be able to get you to a point where you can build and train a convolutional neural network or another type of artificial neural network using one of the available software frameworks. More generally, the mathematics of deep learning is not actually incredibly complicated. The prerequisites you typically want to have if you want to understand the mathematics of how a deep neural network is trained would be basic linear algebra, particularly matrix algebra. That helps you understand how the feed-forward process works. Basic calculus if you want to understand how the stochastic gradient descent training works under the hood. But it's rarely necessary to apply that knowledge in applications if you're going to use existing standard network activations and objective functions. Understanding optimization techniques is also helpful, but not critical. If you do want to move further into the research aspects of deep learning, some complementary materials to what will be presented in this course that I like to use are shown on the slide I just changed to, useful links for machine learning and deep learning fundamentals. Andrew Ng's Coursera course on machine learning is very good for understanding machine learning processes in general and the training of machine learning models. The Stanford CS231N course on convolutional neural networks will add some more depth, will complement the practical approach we're taking with some more of the mathematical depth on convolutional networks. And the tutorials made available by the Fiano developers do a great job of mapping the mathematical explanation of an artificial neural network structure to the code implementation and showing how you would do that in Fiano. There was a question, are any of the recent algorithm advances already baked into the deep learning frameworks, or is it up to the user to choose the correct pre-processing methods and implement them outside the libraries? It depends on what you mean exactly by algorithmic advances, but the deep learning frameworks are very actively developed by large open source communities today. So often the first time that a new algorithmic advance or an advance such as a new type of activation function, a new layer type, the first time that appears will often be in one of those deep learning frameworks because the academics who are developing those advances are often using those same frameworks. So as an example, if you wanted to build a state-of-the-art convolutional neural network that used rectified linear units for activations and dropout for regularization, and allowed you to apply data augmentation when you input your data, those features are all baked into the deep learning frameworks to some extent. So you can certainly build modern, highly performant deep neural networks using those deep learning frameworks. So, one question, there's a question about slide 7 in the webinar, which I believe is this slide. The numbering, sorry, has changed in the bottom right corner. The question is, how do we find the errors? Is that based on any model or user input? So the deep learning approach, which we showed on this chart, is what's referred to as supervised learning. Supervision means that the input data has associated ground truth labels. So in this example, the input data are images of animals. The ground truth labels are these labels: cat, dog, honey badger. The errors are automatically computed by the neural network by comparing the prediction it makes, which is made without the use of those labels, to the actual known ground truth label. So for example, if the top layer of the neural network is a 4-dimensional vector trying to predict dog, cat, honey badger, raccoon, then when you input one of the images, that vector will come out as a probability distribution for those different classes, and you can just take the difference between that probability distribution and the known truth, i.e. that the vector should be a 1 for the correct animal and 0s elsewhere, and that gives you a quantitative measure of the error. You then use a method which we haven't talked about yet, but will be seen in the subsequent classes, called backpropagation, to map that error back to each of the layers in the network and determine the modification that you need to make to the parameters of each of the layers in response to that error. Another common question that we received last week was, are neural networks, deep neural networks, always trained in a supervised fashion, in the way I've just described, where you have labeled data, or can you also train them in an unsupervised fashion? So indeed, you can train them in both ways, supervised and unsupervised. The modification that you make if you don't have labeled training data is that you have to change that top-level objective function where the error is determined, because now you don't have the ground truth correct labels to determine whether the prediction your network has made is useful or accurate. So instead, you come up with an error function that in some sense determines whether the network is making desirable choices for the weights. What I mean by desirable choices is, if you input a large number of images to the network and without labels, one objective for doing that might be to have the network be able to cluster those images based on visual similarity. So the objective function that you input at the top could be some measure of how well the data is clustering and how well different clusters are being separated. This is typically not as effective an approach for coming up with clustered classes as having labeled data, but it can work well. Another common approach to unsupervised training, which you may have come across, is called the autoencoder. In this approach, what you do is you input your data sample, for example, an image. You reduce the dimensionality of the data using the deep neural feed-forward process of the deep neural network. You then attempt to recover data of the same size as that original input sample, and your objective function is to compare how well your reconstruction, how close your reconstruction is to the original input data. And again, this can learn to find a dimensionality reduced representation of the data, which helps you determine when images are similar or images are dissimilar. So autoencoders are another approach to unsupervised training. Okay. One question on practical training of deep neural networks with GPUs. Can a normal desktop with a video card train a reasonable deep neural network, or do you need Google-sized resources to leverage this technique? So for example, could you use a GTX 980 for a convolutional neural network? So yes, indeed, many deep neural networks will fit onto a single GPU, a single consumer GPU in a desktop computer. The results I mentioned last week, where there was the sudden drastic improvement in the performance on the ImageNet challenge, were trained, those convolutional neural networks were trained using commodity consumer GPUs, GTX series GPUs in desktop computers, and it's still relevant today to be able to train highly effective GPUs and consumer cards. Our current best consumer card for this is the Titan X, which has 12 gigabytes of RAM, which is certainly sufficient for training many effective models. Once you move to a more serious deployment where you're using servers and you perhaps have much higher data volumes coming through for your production system, then you would want to move to the server-side Tesla GPUs. Another frequent question we received was, once you have trained a network, can you adapt it to a new set of data? So for example, could you add a new classification category? So this actually works very well, and the method is called fine-tuning or transfer learning, depending on exactly what you're trying to do. So one example is that if you had already trained your network on an image data set, and then you got a new set of images which introduced a new class, what you could do is you could fix the weights for the lower layers of the neural network, because these are likely to still be very close to the optimal weights that you'll learn for your new class if it's of a similar type of imagery. But then you can actually fine-tune the upper layers of the network with your complete data set, including your new class and new training samples. And so at that point, you can modify the top layer in the network to include your additional class. And that can be a very effective way of actually very quickly modifying the network to incorporate that new information and be able to discriminate that new class. Another closely related method is called transfer learning, where instead of fixing the weights and then fine-tuning the network on the same set of data with some additions, such as a new class, you instead fine-tune the network on an entirely different set of data which was never used in your original training. Typically, this entirely new set of data would be of a similar sort of data. So if you had images of animals, you might move to train on images of people. But again, the lower level visual features, pixel level features, small oriented edges, etc., will be very similar between those two data sets. So that transfer learning approach can mean that you can very quickly fine-tune the network, the upper layers of the network against an entirely new data set without having to relearn all layers of the network. Another benefit of that approach is that that second data set can typically be much smaller than the original training data set. You can even often train a second data set with just hundreds or thousands of examples when you're just trying to fine-tune that final top layer. One more commonly asked question this week and last week was, can deep learning be applied to non-classification problems? Most of the examples I talked about were supervised learning, where the input data had some class label associated with it. again, in the same way as I described training deep neural networks in an unsupervised setting where you modify the objective function, you can also do this still in the supervised setting, but for non-classification problems such as a regression problem. So in a regression problem, instead of trying to predict which class from some finite number of classes your input data belongs to, you're trying to predict some continuous quantitative value. So an example might be, that you might have seen recently that was covered in the media, was Microsoft delivered a web service where you could upload a picture of yourself and the service would predict your age. So that's kind of a continuous prediction of a value. And indeed, it's a relatively trivial change that you make to the objective function to address a problem like that. Okay. One question commonly received, what pre-processing is usually applied to data before being fed into a deep neural network? You almost always will subtract the mean value for each of the features in your input data. So for example, for each pixel across your entire data set. So just to make that clear, you take your entire training data set, but not your validation or test data sets. And for each pixel, you subtract the mean value across each of the training images. You can also do this if it's not imagery data, any real valued feature vector that you're inputting into your neural network. You can do that same mean subtraction operation. Often you also standardize those values. What I mean by that is also dividing by the standard deviation. This can aid with convergence of the training of the network. For non-imagery data, people often apply dimensionality reduction techniques such as principal components analysis. I won't go into the details of that. It's beyond the scope of the course, but you typically wouldn't do that for imagery data. One important step in pre-processing is that if you have a large number of training data samples, so for example 1 million images, as I've mentioned, you typically train your networks in smaller batches of maybe 100 images at a time. You want to make sure that those batches are well stratified across your classes that you're trying to predict in a classification problem. So what I mean by that is you want to ensure that your first batch isn't all dogs and your second batch isn't all cats. The reason for that is that you run the risk if you do not do that stratification across classes, you run the risk of your optimization becoming stalled in local minima for the objective function, or in the best case, just much slower convergence for the objective for the training, because the objective function will kind of meander more through the objective space. And finally, I mentioned a moment ago that you would also have a validation data set. What I mean by that is that often you don't take all of the labeled data you have for training and train your network on that, because then during training you have no idea how well the network is going to work on new previously unseen test data. So what you typically do is take a subset of your training data, maybe 20% would be typical, and you intentionally do not train your data on that 20%, even though you do know the true labels for that data. Because then, as you go through the training process, you can periodically check the performance of the network on that held out validation data, and that's equivalent to having a good idea of how well your network will generalize to new data samples that you might encounter when you go into production and try and deploy your system. Another common pre-processing step that people take is what we call data augmentation. I think I mentioned that earlier. As I've alluded to, the two real challenges you face with training a deep neural network are called overfitting and underfitting. Underfitting means that your network doesn't learn accurate prediction even for your training data. And overfitting means that your network is really good in your training data but not very good on your test data. The cause for underfitting is typically that you don't have a large enough model, as I mentioned, so you can just increase your model size. Overfitting, one common method to control that is this data augmentation pre-processing step, where what you do is you artificially increase the amount of training data you feed to the network, but you do it using plausible corruptions of the data that you will encounter in the real world. So for example, you flip the images, you rotate them, you may add Gaussian noise or some other type of noise. And those augmentations mean that your network effectively gets trained on a much larger data set. Even though some of it is synthetic, it should be very similar to what you would expect to encounter in the real world, and the network therefore learns to generalize better to previously unseen data. So yeah, there are many approaches to pre-processing, and if you look at some of the recent papers on deep learning successes through the links I provided, you will certainly see a variety of pre-processing steps being applied. So another question here is, how stable are the weights of a network during training? If you continue to add more and more training data, will the weights constantly fluctuate, or are they guaranteed to converge, perhaps within some small bound to a stable value? So there's two-part answer to that. If training is proceeding successfully, then the weights will fairly smoothly move towards an optimal set of weights for the task at hand. This isn't guaranteed at all. No, there are cases where the weights can do two undesirable things. One is that they can stall. They can stop changing. This is due to a problem called vanishing gradients. The specific details of vanishing gradients is a little bit beyond this Q&A today, but essentially what it means is that the changes that the error function is causing to be made to the weights become infinitesimally small and the weights just stop changing. Or there's an exploding gradients problem, also sometimes called unstable gradients. And what that means is that the weights become very large, and so the changes to the changes to the weights that need to be made become very large, and so the weights themselves become very large, and your error actually increases and you converge away from some optimal. The way you control for this is there's a number of different parameter choices that you need to make when you're constructing a neural network to control for this. One is called the learning rate. So that is a measure of how much you update each of the weights relative to the error that was made on your last training sample. So that's a parameter that you have to fine-tune manually throughout training. Another important choice you have to make is how you initialize the weights in your network. So one thing you don't ever want to do is initialize your weights to all be zeros. They will never learn anything. You typically initialize them to be very small random numbers, so small being much less than zero, a decimal number, a positive real number less than zero. But again, there are many different approaches to that initialization, and so it can often be an iterative process where you watch your network train for a little bit, see if the weights are converging, and if not, make some modification to one of those parameters I mentioned so that you can then get that convergence. And a tool like digits is good when you're first getting into training networks for being able to see in real time how the error is converging, how the weights are changing, so that you can learn to make those modifications to the parameters. Okay. Question, I just mentioned digits again. We had a specific question last week related to digits which didn't get answered. Does digits include debugging tools? For example, can you check your gradients and activations along many iterations? So you get the visualization tools I just mentioned, which show you how your error is changing and can allow you to inspect what the weights you have learned in the network look like so far. But beyond that, there are no debugging tools to help point you in the direction of how you should modify the network to get better performance. But that's definitely an excellent suggestion for a future feature. Okay, another question. How can you leverage multiple GPUs to train a single deep neural network? So again, this is very much an ongoing research topic, the best way to do this. But at a high level, there are two approaches that are taken. One is called data parallelism, and what this means is that you take your very large training data set, you distribute it across the multiple GPUs, and then you train separate neural networks but with the same architecture on each of those GPUs, and then periodically during training the parameters of the network are exchanged communicated between the GPUs so that each of the networks becomes some combination of all of the networks. That's data parallelism. Obviously, a challenge with implementing that is this communication cost that you incur between GPUs. Another approach is called model parallelism, and in this case, you actually break up your neural network across GPUs, but train each of the subparts of the network on the complete data set, and then you again have a challenge in parameter exchange there. So there are two approaches that are still very much hot topics of research. How many epochs do you typically train a network for, and when do you stop? So if I haven't used it already, the term epoch is used interchangeably with iteration. What an epoch or an iteration typically means is that each of your training examples has been fed through the neural network once. A typical number of epochs, iterations, would be, so 1,000 would be a typical number, but I'm not suggesting that that is the number you should choose. The way in which you should choose how many epochs you train for is to monitor the performance of the network against both your training data and against your held out validation data as you train. So maybe after every 10 epochs or 100 epochs, you measure the average performance against your training set and your validation set. And when you find that your performance against your validation set is no longer improving, but your training set you may still be improving, then that is when you should stop training, because you are starting to overfit. You're starting to see benefits against your training set, but not against your validation set. So yeah, there's no clear choice as to how to choose how many epochs, and indeed you wouldn't want to just fix a number. You want to actually monitor how training performance goes over time. Okay. For time series classification, should I use convolutional neural networks or recurrent neural networks? So I mentioned recurrent neural networks very briefly in the last talk. I've just changed to a chart which shows a kind of toy picture of a recurrent neural network. Just to recap, the difference between a recurrent neural network and other types of artificial neural network, not just convolutional neural networks, is that you have this connection shown in blue, which I'm just trying to highlight, which connects the hidden layers of the neural network back to themselves. What this means is when you input a new training data sample, as well as receiving that training data sample as input, the hidden layers receive what their state was the last time they received a training data sample. So this effectively gives the network a memory. So for time series classification problems, this is typically the optimal approach today because you can actually model temporal dependencies over an arbitrary time frame that appear in your time series. You wouldn't typically use a convolutional neural network for time series classification unless there really is also some spatial correlation that's important. So what I mean by that is if you have a one-dimensional time series, a convolutional neural network is not necessarily meaningful to apply. But in cases where you have, for example, an audio data, which is intensity in different frequency bands over time, then there is a spatial component that's important, and you can indeed treat that time series as a kind of image and apply convolutional neural networks. And there's been some impressive examples of people taking an approach like that to classify genres of music, for example. But recurrent neural networks are the most obvious logical fit for time series prediction problems. Okay. Can models be deployed with a reasonable runtime on a machine that does not have a CPU, that does not have a GPU, that is CPUs only? So you can always do both training and deployment and classification with and without GPUs. For training, GPUs have become the de facto standard. The reason for this is that to typically manage the large volumes of data that are needed and the large network size that is needed to get accurate prediction performance on that data, it wouldn't be practically feasible to train on a CPU-based system. It is certainly possible. I gave the example last week where Google trained their Google Brain neural network, which had a 1 billion trainable parameters, and they used 1,000 CPU servers with a total of 16,000 cores. But unless you have the resources to build systems of those sort of sizes for many real-world deep learning applications, it's going to be impractical to train on CPU, and GPUs give you that physical footprint advantage, speed advantage, and cost advantage. For deployment, it's much more feasible to deploy onto a CPU-based system. The individual feed-forward operation for testing a new data sample is a relatively computationally cheap operation that can be executed on a CPU-based system, but there still is advantage to GPU-based processing for deployment if you have a large and constant stream of test data that you want to deploy, or you have very large individual test data inputs. You can still see a speed-up advantage for GPUs. So for example, if you wanted to use a convolutional neural network approach against real-time video, you would definitely see a benefit of using GPU acceleration for deployment. Okay. I guess a related question that we had a few times last week Can deep learning techniques and algorithms be deployed on FPGAs instead of conventional CPUs and GPUs? So these are field programmable gate arrays. Yes, they can. The challenge you have is that it's very hard to update the network structure, the parameters that are used in a neural network if it's on an FPGA implementation. With a GPU implementation, you have general purpose reprogrammability, so you can very easily modify the network structure to iterate over different designs and adapt the learning algorithms as better techniques are discovered over time. One question about why is OpenCV not on our list of deep learning frameworks? OpenCV, very powerful, very commonly used package for computer vision tasks. Many of the pre-processing steps I mentioned earlier, the data augmentation, you could perform very effectively with OpenCV. OpenCV doesn't natively offer deep neural network kind of scaffolding code that allows you to construct and train deep neural networks. So OpenCV is a very complementary package to the deep learning frameworks, but isn't today directly a deep learning framework itself. Okay. Question specifically to the implementation of deep learning techniques on GPUs. How are GPU cores handled in deep learning? Do you use the same concepts of threads, blocks, and grids like in CUDA? So yes, you do. Under the hood, any of the deep learning applications or toolkits, Caffe, Torch, Theano, for example, that leverages GPUs is relying on CUDA and their programming model that's described there with threads, blocks, and grids. And that's precisely how they get that accelerated training performance. With cuDNN, the NVIDIA library, CUDA library I mentioned in the webinar that's specifically aimed at deep neural network training, we have released highly optimized versions. A lot of the computationally intensive operations that are performed in deep learning training, and again, those adopt that same CUDA programming paradigm. But the good news is that again, much in the way that if you want to be a practitioner of deep learning and develop a deep neural network against your own image data set, you don't necessarily need to understand the calculus behind stochastic gradient descent training. You also don't necessarily need to understand the implementation of those lower level convolutional neural network functions in CUDA. A lot of that is abstracted away for you by using the software frameworks such as Caffe, Torch, and Theano. And even when you go to digits, it's further abstracted away to allow you to build these networks using a graphical interface. So I would say that again, unless you are a software framework developer or you are a researcher looking at the low-level optimization of deep learning functions, you don't necessarily need to understand that CUDA implementation model. Okay. Another question that came in more recently was, are there any books of deep learning with exercises? There are many books. I am not going to choose any particular ones to highlight at this point, but I'll again show my chart from earlier of useful links on machine learning and deep learning fundamentals. So Andrew Ng's Coursera course, the Stanford CS231N course on convolutional neural networks, and the Theano deep learning tutorials. Each of these courses gives you both examples of the mathematics of deep learning, examples of the implementation in code, and exercises which you can try yourself to test your knowledge of those concepts. And then obviously, as we go forward in this course, the hands-on labs will become increasingly interactive, requiring you to make modifications to the code, see the actual implementation of the network, and get those examples of how you practically apply deep learning to different data sets. Okay. Given a GPU with a fixed amount of RAM, how do we know the correct way to choose the batch size? Is there a mathematical formula by which to know what is the memory usage of backpropagation and thus select the optimal size? Not strictly, no. There isn't a formula I can easily quote on a single chart for doing that. Typical values for batch size are in the low number of hundreds, so maybe 100 training examples per batch. That's certainly not fixed. It's very dependent on the size of the individual training examples, the number of trainable parameters in the network, and so it's really another parameter which you want to look in the literature for typical values used for a similar network, similar data, and then monitor your GPU memory usage and training time during training, and then modify those batch sizes in response. Just to follow up on the OpenCV question earlier, is CUDA based on OpenCV itself? No, CUDA is not based on OpenCV. They are entirely separate software packages. Okay. I have time to answer a couple more questions. One common question last week was, what examples are there of deep learning being applied outside of vision, speech, and natural language understanding? So the answer is there aren't a huge number of examples outside of those areas. And the reason is that deep learning really excels at these perceptual tasks based on very complex raw data inputs. But there are some examples in the medical field, for example, in the discovery of potential drug interactions. The formulation, I believe I mentioned this last week, the formulation of a general multi-layer artificial neural network allows the input data to really be any real valued feature vector. So you can certainly train a network on more structured data, non-vision, speech, or natural language data. Typically, deep learning excels when the function which maps that data to the objective is very complex and would be very hard for you to hand code. So for all of these reasons, there's not a huge number of examples outside of these sensory perception tasks, but there are very broad applications that use those sensory data inputs for very varied applications. Okay. And I'm going to answer one more question before we wrap up. And that is, can I talk about the advantage of using batch processing? So it says, the asker of the question said, I'm using Caffe. It seems batch processing has no benefit with CPUs. So that's true. If you're using CPUs, you're by default, within Caffe, you are going to be typically doing sequential processing, so one input data sample at a time. So there isn't necessarily an advantage of batch processing. That's not entirely true, as you would still see a performance improvement more generally in training a deep neural network if you used batches, because you could vectorize the mathematical operations which are feeding those data samples through the network. The big advantage of batch processing when you have GPUs is that you can exploit the massive parallelism on the GPU to simultaneously train each of those input data samples in the batch. the choice of this batch size, just to add to my answer to that question earlier, will affect the rate at which your training converges, because you are receiving less, the larger the batch size you use, you are receiving less updates to your network weights per input data sample. So again, the batch size is a parameter that you want to choose based on how well your network is training. So at that point, we have come to the conclusion of the Q&A session. The next class we have lined up is getting started with the Digits Interactive Training System for Image Classification. My colleague Alison Gray will be presenting that class next Wednesday at 9 a.m. Pacific Standard Time. I look forward to seeing you all there. Many thanks.